Come back. So now we start with computation formula for R. Now, how to compute the sample coefficient, correlation coefficient R. For n data pairs xy, they should have a bivariate normal distribution. This means that for a fixed value of x, the y value should have normal distribution. For a fixed value of y, the x values should have their approximately normal distribution. Okay, that's a prerequisite to start. Take the sum of x, take the sum of y, take the sum of x squared, that is square all the x's then or add them up. Take the sum of y squared, that is first take all the squares of y's and then add them up. Lastly, take the sum of x times y, that is for each pair xy, multiply xy and then add such products up. N is the sample size. You have all these sums ready and now you're ready to compute R. R is a big fraction. Numerator consists of n summation xy minus summation x times summation y. Denominator is square root n summation x squared minus summation x the whole power 2 times square root n summation y squared minus summation of y the quantity squared. Be careful, the notation summation x squared means first square x and then add them up, as opposed to parentheses sum x squares means first add them up and then take power 2. All right. Now, once you have such information, you have the possibility, interpretations. It can be shown mathematically that R is always a number between positive 1 and negative 1. Now, here is a quick summary. When R is 0, there is no linear relation among the points. So your points are all thrown all around. If R is 1 or negative 1, there is a perfect linear relation between x and y values. All the points lie on the least squares line. So R is negative 1, you're going down. R is positive 1, you're going up on a straight line. That's perfect linear relation. Now, R is between 0 and 1. Okay, between 0 and 1. That is, you have a line, but all your points are not exactly on the line, but they are close to the line. Okay, the x and y values have a positive correlation. We mean that large x values are associated with large y values, small x values are associated with small y values, and as we go from left to right, the least squares line goes up. On the other hand, if R is between negative 1 and 0, right, then the x and y values have a negative correlation. By this we mean large x values are associated with small y values and small x values are associated with large y values. As we go from left to right, the least squares line goes down. Sand driven by wind creates large, beautiful dunes at the Great Sand Dunes National Monument, Colorado. Of course, the same natural forces also create large dunes in the Great Sahara and Arabia. Is there a linear correlation between wind velocity and sand drift rate? Let x be a random variable representing wind velocity. it is 10 centimeters per second, and y be a random variable representing drift rate of sand, 100 grams per centimeters per second. Okay, so many grams per centimeters, that's the amount of second moving that's the amount of grams of sand moving each second. Now, a test site at the Great Sand Dunes National Monument gave the following information about X and Y. Okay, so here is X and here is Y. All right. Now let's plot these points. You see, it looks like positively correlated, but they are not perfectly correlated. That is, they are not all in a straight line. In fact, they seem to be more like on a curve. We can draw a line, a best fitting line. Okay, so this is your scatter diagram. From the scatter diagram, it appears that the X values increase, Y values also tend to increase. So you're going to expect your coefficient of correlation to be positive. All right. So here are the calculations. You have X values from the table, Y values from the table. Now square each X value. Square each Y value. Take X times Y, multiply these guys. Once you have these, add them all up. That's summation X, summation Y, summation X squared, summation Y squared, summation XY. Okay. Next, you are going to plug into these values. You had 7 points. I hope it's clear. You have 7 points. 1, 2, 3, 4, 5, 6, 7. So you're going to use n equals 7 and simply punch in all the values until you get something. Look at that. It is a positive number less than 1. Okay. You will always get a number between -1 and 1. But if you remember your diagram, it was positively correlated. So you are going to get something greater than 0 less than 1, which is what you got. Okay. Using a direct calculator, you can also find this. Okay. What is the value of R tell you? Since R is very close to 1, you see, it's very close to 1. We have an indication of a strong positive linear correlation between wind velocity and drift rate of sand. In other words, we expect that higher wind speeds tend to mean greater drift rates. Because R is so close to 1, the association between the variables appears to be linear. Because it is quite a task to compute R, for even 7 data pairs, the use of columns is extremely useful. Your value of R should be always between -1 and 1 inclusive. Use a scatter diagram to get a rough idea of the value of R. If your computed value of R is outside the allowable range, or if it disagrees quite a bit with the scatter diagram, recheck your calculations. So if you find an R which is 2 point something, well, you're not allowed to go to 2. Your R must be between these two. If your diagram says it's going up, then R has to be positive. If your diagram were to show going down, then R would be negative. If your diagram is all over the place, you expect R to be closer to 0. If your diagram is closer to a line, your R will be closer to +1 if it's going up, -1 if it's going down. So these are intuitive ideas you need to know, which will help you detect any errors in R. Be sure to distinguish between expressions such as summation x squared and summation x power 2 to power 2 should be outside. So these are different things, right? Negligible rounding errors may occur depending on how you or your calculator round. Of course, depending on your calculator or your computer, your rounding will be different from, say, somebody else doing the same calculations. Okay, so this completes the lecture slide for section 4.1. Next video will go over problems from section 4.1. Until then, bye.